So in this video, we'll talk about the topics of improper integrals. It is a special type of definite integrals. Please look at the following picture and examples. So let's look at the current picture now. Let's say I'm giving you a positive function y equals f of x. You see the purple line is always staying above the x-axis. If I try to measure the area, which is based on the shaded part starting with the line x equals a, all the way up to the right hand side, which means you keep going on. So as you can see, it's kind of like an unbounded region, right? And we don't really know how to measure this area if you don't know anything about the integrations. But let's think about it this way. Based on a previous video when we described the definite integral, we understand that we can measure this area based on the integration from a to infinity for the positive function f of x, right? And this infinity means what? This infinity means you actually don't have a right endpoint that bound the shaded area. So as you can see, the region is unbounded. So it keeps going on forever to the right side. So we can say the upper limit b is actually infinity. And now let's come back to the mathematical meaning of this notation. As you can see, obviously, there's a chance that the area can be infinite, right? But there's still a chance that the area can be finite. So let me put it here. So basically, there are two possibilities here. We don't know whether the area is finite or the area can be something infinitely large, right? So we have to do the calculation for this integral. And mathematically speaking, we have to be careful about this notation because of the fact that there's a chance that the area is infinitely large, which means this notation is actually not well defined, right? So let me write it down here. So please look at the red box. In the case that the second possibility occur where the area is actually infinitely large for the shaded part, and this one, numerically speaking, does not exist because it is infinite. So we cannot say it is a well-defined integral. So we have to be careful about the terminology now. So formally speaking, whatever we talk about in the last page about the improper integral, this one now is called improper integral because it's not the proper integral that you usually see, where the lower and the upper limit are some fixed number, right? Because the top now is infinity. And formally speaking, we can try to define it by using a limit notation by taking b goes to infinity for the upper limit. You can think of it like this, formally speaking. And let's do some practical calculation. So please look at the current problem now, and I trust that quite a lot of you actually understand this graph y equals 1 over x. So I try to put it here. And basically, you see now the improper integral is from 1 to infinity. And essentially, you're measuring the area of the shaded part, which is starting from 1 all the way up to the end. Never stop here. And let's look at how to find this area. And you can imagine that, as I said in the previous page, you can use a limit notation to represent this. And if you are doing it this way, the fact is that you can just do the usual definite integral, right? And because the antiderivative of 1 over x is ln x, so you can do it here. And it essentially means you're doing a limit problem where b is going to infinity for ln of b minus ln of 1. And this one, of course, is 0. So basically, the problem is about determining the limit b goes to infinity for ln of b. And I trust that you have seen this problem already. The answer is conceptually infinity because of the fact that if you look at the ln function, it always increases without any bound here. So it essentially means when x goes to infinity, when you keep going to the right-hand side, ln of x is always going to infinity without any limit because of the fact that, well, the shape of the graph is just like this for y equals ln of x. Although ln x as a function is actually increasing very slowly comparing to other polynomial type functions. But anyway, it goes to infinity. It means that we don't get a well-defined answer to this, or the other way to say it, the area here is actually infinitely large, right? And because of the fact that for some problems, the improper integral is not well defined, and for some of the problems, the improper integral is actually quite well defined as a finite number, so we have to give a terminology to that. So please look at my sentence here. I give a definition here. If an improper integral like the one you did actually give you a fixed number after all the integration process, we call such an improper integral convergent. Otherwise, it is a divergent integral. So it means that based on the last problem, when you do this improper integral from 1 to infinity for the function 1 over x, this one is actually a divergent integral because we got the answer that conceptually it is the same as infinity, right? And let's look at another problem now. How about this case? If I ask you to integrate from 1 to infinity for 1 over x squared, you can try to understand what's happening here, and mathematically, to be very formal, you can use a limit b goes to infinity for the upper limit b to represent what you're doing here. And I trust that you are able to do this calculation because of the fact that 1 over x squared is the same as x to the power minus 2. So it means that you are actually finding the antiderivative of x to the power minus 2, right? And by the power rule, we actually get that it is same as this function. So let's do the remaining steps here. You see, it's much easier to represent the current function as minus 1 over x here. And let's do the limit calculation here. So you're basically looking at something like that. I'm replacing x by 1 for the lower limit, and for the upper one, and there's a minor typo here. I would like to put it b here. I should put it b here. And only the first term in the first bracket matters because this one is just minus 1, right? It's a fixed number. Let's look at the first term. And if you replace b by infinity, conceptually it becomes minus 1 over infinity, which is conceptually the same as 0, right? And it means the limit of this problem is the same as 0 minus minus 1, which is plus 1, which is of course a fixed number, which means that this integral that we have from the beginning is actually a convergent integral. So and let's do one more problem. So if I'm asking you whether this improper integral is a convergent integral or not, evidently is a problem about integration of this function. And if you're able to get a fixed number after the integration, we call it a convergent integral. And let's do the calculation now. Kind of indefinite integral, you're getting this one as the antiderivative, right? And it means that if you look at the top here, what you're getting here should be limit b goes to infinity for something from 1 to b, and this something is actually this antiderivative. And let's look at the next step. Limit b goes to infinity for this one, and the second term comes from the fact that we have to replace x by 1 here, so it is minus e to the power minus 1. And for the first term, it's gonna be x replaced by b is minus e to the power minus b, right? And the second term doesn't matter, it's just a constant. So we only care about the first term. You see, because it is a negative exponent, I can write it as minus 1 over e to the power b. Now the fact is that when you replace b by infinity, conceptually it becomes something like minus 1 over e to the power infinity, right? So it is basically minus 1 over infinity, and which is 0. So it gives you a sense that the answer to this problem after taking the limit b goes to infinity is 0 plus 1 over e, which is 1 over e, which is a fixed number, of course. So because it is a fixed number, after all the steps of computation, we understand that it's actually a convergent integral. That's actually the end of this video.